continue our lesson from the other day on angles. Today our focus is going to be on arc length, specifically how to find the distance of the arc length. We're also going to focus our energy on finding the area of a sector and then end our time with angular and linear velocity. So to start us off, let's recall from our last lesson that we defined the arc length as S, and that this arc length is the drawn out part of the circumference of a circle by a particular angle theta. It is this portion of the circumference between the initial and terminal sides of the angle. We also determined that the radian measure is the ratio, so it was the ratio of the length of the circular arc, which is drawn out by the angle to the radius of the circle. So notice that radian measure theta is equal to the arc length divided by the radius. And depending upon what value we are in need of, we can also find the arc length of a circle by solving this formula for S. Thus, we could take theta equal to S divided by R, multiply both sides by the radius, and thus the arc length can be found by taking the radius times theta, which is this formula found here. So going with that idea, Mercury orbits the sun at a distance of approximately 36 million miles in one Earth day. It completes 0.0114 rotations around the sun. If the orbit was perfectly circular, what distance through space would Mercury travel in one Earth day? So it says that Mercury orbits the sun at a distance of approximately 36 million miles. This is going to be our radius from Mercury to the sun. We also know that one rotation that we learned the other day is equal to 2 pi. I also know that our rotation is going just a little bit under that, right? We're not quite going that distance. Thus, I'm going to want to find 0.0114 rotations and set that to multiply by 0.0114. So we are approximately 0.0716 radians, because we need radians for this formula. Now that we know the radius and we know the radian measure, so this is theta here, and we know the radius, we can find the distance that it's traveling through space by taking the radius of 36 times our radians to determine that we are traveling 2.578 million miles as we are traveling on the circumference of that orbit. Again, assuming that the orbit is circular, even though we know orbits are typically more oval shaped. Example 2 is asking us to find the arc length. Again, we need the arc length. Arc length, its formula is S. Arc length is equal to the radius times theta, which is the radian measure. Find the arc length along of a circle when we are given the radius is equal to 10. Subtended or drawn out by an angle of 215 degrees. So we know, if we're looking at a circle here, kind of drawing a picture a little bit, we have our initial angle, and we're going about 215 degrees to our terminal angle. So this is 215 degrees. Our radius is 10. We want to know what is the distance from where we start all the way around our circle until we get over here. Well, we are in degrees and we need radians. We can find radians by taking 215 degrees and multiplying by pi radians over 180. I'm going to keep this in its exact value because now that I have it in radians, I am easily able to keep it in its exact value by taking our radius times our theta value of 215 pi over 180. We could reduce. We now have the exact value of the arc length. We're not given what kind of units we're specifically in. It just says the radius is 10. It doesn't tell us how, like, is it inches? Is it miles? What is it? So we're going to say once we simplify this to around 37.525 units. Now, depending upon what MyOpenMath wants, does it want the estimated version or the rounded version or the exact value? So we can keep it in its exact value if needed, or we could use the rounded value, depending upon what we're looking for. Let's ponder the formula for what the area of a circle is. We know that the area of a circle is pi r squared. That formula comes from quite some time ago. If we specifically want to find the area of a sector, we have our initial length, our terminal length. We don't know what this length is or the degree values, but we want to find what is the area of this little pizza pie portion. I know then that I could take theta, whatever that might be, and divide it by 2 pi, because this is a fraction of a full circle. Whatever that we're looking for. Thus, I can use our formula and substitute some values in. Thus, our area is given by the fraction of our full circle times pi r squared. Our pi's are eliminated. Thus, we can find the area of a sector by taking half times our degree value, our theta, times r squared. So the full definition, the area of a circle, can be found with a radius r drawn out by an angle, theta, measured in radians. So let's put this to work with an example. An automatic lawn sprinkler sprays a distance of 20 feet while rotating 30 degrees. What is the area of the sector of grass that the sprinkler waters? So let's think about this. We have our initial side. We're only going 30 degrees. Our sprinkler is spraying 20 feet. It's going around. We want to know, what is this area covering? How much grass is actually being watered? Our area is given by half times theta times radius squared. Notice we need radians. We are given degrees. So radians can be found by taking our degree value times pi over 180, which is pi over 6 radians. Now we can use our formula, half times our radians of pi over 6 times our radius of 20 squared. It makes sense in the context of the problem to find out what is the area, how many square feet it is, instead of leaving it in radians in its exact value. So this sprinkler will cover approximately 104.72 square feet. In central pivot irrigation, a large irrigation pipe on wheels rotates around a center point. A farmer has a central pivot system that has a radius of 400 meters. If water restrictions only allow her to water 150,000 square meters per day, what angle should she set the system to cover? Well, in this particular case, we are given the area. We are also given the radius. We are looking for the degree in which she has to hit. So if I think about our initial side, we know that this sprinkler is going 400 meters. We know, we'll just say maybe here, we'll just kind of guess. We need to know what our degree value, what our radians are. When we know that the total area that it's covering inside here is 150,000 square meters. So we can use the formula to help us find radians. Once we know the radians, we can turn that into degrees. Using our formula, our area is 150,000 equal to 1/2 times theta. We don't know what theta is, but we do know our radius is 400 meters squared. Starting to solve for theta here, 150,000 is equal to 400 squared times half is 80,000. Theta, divide both sides by 80,000. I have 1.875 is theta. So this is radians, right? This is in radians, theta is in radians. We need degrees. Thus, I will multiply 1.875 times 180 degrees over pi radians. And I'll get approximately 107.43 degrees. So our particular farmer with a radius of 400 meters should set her central pivot irrigation system to water 107.43 degrees in order to only utilize the allotment of water at 150,000 square meters per day. The next thing we need to talk about to end our lesson is to talk about angular velocity, which is the speed we're going in a circular pattern, and linear velocity, the speed in which we're going in a straight manner. It says that as a point moves along a circle of a radius, so we're thinking of like a tire or a car tire or a bike tire or pickup tire, those kinds of things, can be found as the angular rotation theta per unit of time. So angular velocity is equal to radians divided by time. And angular velocity is found with this really weird W looking like thing. So we have radians over time. The linear velocity V, so V, of a point can be found at a distance traveled arc length, S, per unit of time. So linear velocity can be found by taking the arc length divided by time. In example 5, before we go to the next part here, a water wheel completes one rotation every 5 seconds. Find the angular velocity, so it's telling us we need the angular velocity in rotations per second. I know that one rotation is equal to 2 pi radians, which they're able to do in 5 seconds. I also know that angular velocity can be found by taking the pi radians. It's doing one rotation. We said that one rotation is 2 pi in 5 seconds, the time it takes to do that. So it is traveling approximately 1.257 radians per second. You could even turn radians into degree values to kind of get an idea of where it's traveling, at what speed it's traveling. But this also leads us to wonder what would happen if we were to combine the definitions above with the arc length of the equation. So our arc length, the definition coming from the previous slide, our first slide, when we combine it, we notice that there is a relationship between the angular and linear velocity. So let's take a little bit of a look at this. So the angular velocity equation can be solved for theta, giving us theta equal to Wt. So if I looked at the angular velocity equation, W equals theta over time, and I solve for theta by multiplying both sides by time, theta can also be the angular speed times time, which we get here. I also know that if I look at my arc length definition, r theta, excuse me, what would happen if I substitute the arc length with what I just found here? So arc length can also be found by taking the radius times the angular velocity times time. Finally, if we substitute this into the linear velocity equation, notice our linear velocity is s over time. We just found a new version of s. And let's put this over time. So let's say velocity, oh, here it is. Velocity is rwt over time. We can solve and simplify by eliminating t. Thus, linear velocity is also equal to the radius times the angular velocity, which means that when the angular velocity is measured in radians per unit, linear velocity and angular velocity are related by the equation linear velocity can be equal to the radius times the angular velocity. So different ways in which we can combine these together by solving for one or the other and combining things together, if you will. I encourage you to play around with it a little bit. So a bicycle has wheels that are 28 inches in diameter. Let's stop right there because everything we've done has been in a radius. So I'm going to say that the radius we know then is 14 inches. A tachometer determines that the wheels are rotating at 180 revolutions per minute. 180 revolutions per minute is going to be our angular velocity. And we said that angular velocity is this W piece, so let's hang on to that. Find the speed of the bicycle as it travels down the road. As it's traveling down the road, that's linear velocity. Is what we're looking for. All right, let's talk about some other things here that we're looking at. I know that I can do 180 rotations or revolutions per minute. I also know that 2 pi radians is the same as 1 rotation. This then gives me 360 pi radians per minute. Taking what we learned up above, I can find the linear velocity by taking the radius times our angular velocity. This gives me then 14, our radius, times our angular velocity of 360 pi per minute. Keep in mind that 14 is in inches. So when we simplify this, we have 5,040 pi inches per minute. This doesn't make much sense, right? Because you don't specifically say that you are going inches per minute when you're telling somebody how fast you're going. So we definitely need to convert this into miles per hour, a more reasonable idea of how fast we are going. So how fast is this? Now I'll convert 5,040 pi inches per minute. I know that there is 1 foot in 12 inches. I know through a quick Google search that 1 mile is 5,280 feet. So now my feet are eliminated. And I also know that there are 60 minutes in 1 hour. So I can get rid of my minutes here. Thus, I'm going approximately on my bicycle 14.99 miles per hour. That is our linear velocity at how fast we are going. Our last example then. A satellite is rotating around the Earth at 27,934 kilometers per minute at an altitude of 242 kilometers above the Earth. If the radius of the Earth is 6,378 kilometers, find the angular velocity of the satellite. So we're looking for W. That's the angular velocity. I know Earth, and I know a satellite is going around Earth. Excuse me that it's not perfect circles here. I apologize. We know the radius of the Earth, and we know the distance from the Earth to the satellite. So my radius can be found by taking the radius of the Earth plus the distance of the satellite, and that gives us 6,620. So we found the radius. I also know the linear speed at which I'm traveling. It tells us that it's going around Earth at 27,934 kilometers per minute. So I know the linear speed. Thus, I can utilize the linear speed equal to the radius times the angular velocity to find what I'm actually looking for, which is W, since I know the other two portions. I can now take 27,934 kilometers per minute equal to 6,620 kilometers times W. Dividing both sides by 6,620. We'll see that the angular speed of this satellite is approximately 4.2196 radians. I can say this kilometers and kilometers. So our kilometers are disappearing. And our angular velocity already tells us that it's in radians, not degrees, radians per minute. Of course, you could turn it into degrees if you kind of want to get an idea of how fast that is, but this is radians per minute. Also thinking about that there are 2 pi radians in a full circle. And that concludes the lesson on lesson 5.2 is complete. So you are able to now finish all of lesson 5.2 for your homework.